Hi, thank you very much for having me. I will say I've been part of this community since last year when I received your scholarship to support my work. So it was really helpful. I appreciate you for that. I was thinking of the best title to give my talk today, and I came up with this one. So my work is just here and there. I kind of it's a combination of remote sensing and some modeling and mapping work, which I am into with Jude Casting, who is my PI in my research. So today my topic would be leveraging remote sensing web applications for environmental resource monitoring and hazard exploration. And my work cannot be possible without these wonderful humans who have supported me all the way. Jude Casting, who is my PI, who's funding my research, my advisor, Jingong Lee from the Geography Department, my senior colleague, James Moti, and Amita Mehta, who's also have partnered with her. She's one of the chief NASA scientists, and I will show some of the work we've done. Hopefully, it can help, and you all, anyone who is interested, will be free enough to play with these tools. And then just to mention also, my primary fund is coming from the NSF Arise IPSCOR project. So those projects have been wonderful. And again, the cast, which Jude is the director, have always been helpful. So I appreciate everyone for the support. Okay. So today's presentation, I'm going to try to keep it within the 30 minutes or even less so we can all have time to interact and do some demo. But I want to begin by giving some kind of background as to why this research is important and why I'm doing this research and how it's helping and how it's being used as well. So I'll start by giving an introduction. I will introduce myself properly, and then I will give an overview of two applications here. I want to focus on what there are several of them there. We have the image precipitation extractor, which is a precipitation extract and an application that can help you to get rainfall at 30 minutes interval, which is really cool. We have the PMP calculator for modeling extreme flood, really good. We have the rapid forcing retriever if you need to reanalysis data sets, those wind and the rest of them. This is a cool place to get the data from the North American land system data sets. And then we have the rapid image viewer, which you are all familiar with. So today I'm just going to focus on the overview of image precipitation extractor. I will give an overview of the rapid image viewer and other potential applications like I mentioned there. And then I will just show one or two slides about the current and future research I'm doing. Then we can wrap it up with questions and comments. I had my bachelor's in geography and environmental management from the University of Abuja, Nigeria, before where I was mainly into theoretical GIS and land cover mapping. Then I moved to KU in 2019 to work with Jingong Lee. I had my master's with him in 2021, where my research was basically on probable maximum precipitation. Think of it as a stochastic model of extreme precipitation event. And yeah, and then we use that, which we use to do some extreme flood mapping scenarios and all that. And I started my PhD, which I'm currently working on, and my research in the PhD have advanced. I focus more on web application development, trying to see how I can create support system for other research, looking at extreme weather events. Also, I'm looking at hydrological modeling and mapping, and also I use vast majority of tools there to support my work. So it's been awesome through this journey. So why do we have to develop this web application? That's the question I always get. Why do we have to develop this question? Are we doing all this? So I divided into the what, the why, the what, the where, the when, and the how. And hopefully this will help to narrow down the kind of objective as to why we use this remote sensing web application. So we need to monitor and report changes in environment. And we know that institute data are not always everywhere, right? And so we can leverage on the power of the satellites and other remote sensing technologies to retrieve this information and help us know what's happening in our environment. Also to understand the climate change impact on Earth resource. So everything is tying down to climate change. How is the environment changing? So we have indicators from vegetation change and all that. We want to also provide complementary data to support models and institute measurement, because we know, for example, when we talk about the rain gauges, which we use to model discharge, they are not abundant everywhere, and we have gaps. So we can use those data and satellite data to complement them and see how we can bridge that gap. Right. We also want to study variations and intensity of hazard in certain locations. We want to know why there are patterns across our regions. Why do we have these events happening here? Why do we have wildfire here? What areas have been impacted, right? Want to explore when the event happened and plan for future occurrence, and how can we communicate the information to consumers, right, which are the general population. These people are not program oriented. They may not be so programming. But so the web application is simple. We don't need to write any code. So we do those behind the scene and let you monitor events. And that's one of the objectives for these tools are helping to achieve. So I want to start with the first one, which is the image presentation extractor, and then we can move into the rapid image viewer and make progress from there. So in 2022, NASA came up with this GPM mentorship program. They kind of collaborated with suicide scientists across universities and those also working in their centers, try to see how they can make effort to enhance the current precipitation, or how they can talk about model evaluation, talk about even the evaluation of the precision products and how all these can be improved, right? So they also work with students, and part of what students have to do is to create projects, what they can do in their project. For me, what I found that I could do was I needed, so in 2023, I didn't join 2022. In 2022, I was with NOAA doing my internship in Alabama, and in 2023, I had a short period of time between March and May, June. I was able to squeeze in few time to attend and see what I can do for them. And what I found was that their existing sources takes a lot of efforts to retrieve the precipitation, right? And then I needed something that have easy for global coverage. And also we can also track storms and see how we can find anomalies, annual anomalies, how precipitation anomalies is deviating from annual average, right? So we can know what's going on, help for climate change. So I went into this full scale extracting image time series data, and then calculating monthly deviation from the time series and tracking the storms. Again, my effort was to do this at a global scale, but then I had to also validate using some watershed I trust I have station data, which is a watershed in Connecticut, to do some evaluation to see, okay, what is the precipitation here? If I use the precipitation from IMAX to run models, what would be the kind of, how would the result compare with the USGS stream flow discharge? And that was basically how I tried to test the output from my IMAX precipitation extractor. And how the data set, the image data, which I need to talk about, the image data inherited the trim data set, right? It's have a 30-minute resolution, so we can the satellite can collect data from multiple. That's the word image, which means integrated multi-satellite retrievers for GPM. So we can take precipitation estimates from all the satellite and also use GPCP ground station to optimize and make sure that what we are estimating is relatively at par with what station we see at the station, which is really cool. So I did that. I used that. I was able to use Google Earth Engine to build this web application, and we are focused on looking at the daily data. So we have the monthly, and also make sure I focus on the calibrated band, and that is what, so I don't to reduce the uncertainties that comes with using remote sensing data for this such analysis. So basically what we need to do was simple, right? I need to develop a kind of web application that will let users to draw their area of interest they want. It could be point, it could be watershed, and then you could select the date range, and you could send a request to pull out precipitation from 30 minutes up to 1 week. So basically we are converting the 30 minutes data into longer duration. So we're aggregating along the duration. It depends on what you want. And also we can see the storm. If you take those images, we can create some what we call the storm tracking capability, where we can see the kind of storm. Is it cyclonic or anticyclonic, depending on the movement? And we could see the path of the storm, and we can also download this precipitation in form of CSV Excel, and also we can get the average TIF in case you want to use for GIS for some analysis. So basically, this tool was able to do some of that, and this is the interface of what we end up getting, which is the image precision extractor. So you can see here we have where users can load in. So these are we have the USGS gauges. We also have gauges from the NOAA, which is global, and we have watersheds that range from the CONUS down to global watershed. And you could be able to digitize your watershed areas and give in the input for the start date and end date, and you can tell it, send the request. Do you want to get it in 30 minutes? Do you want to get it in 1 hour? Do you want even up to 1 week? It's going to give you the data, and this is an example of how the data looks like. And you can also download it, which will come as zipped GeoTIFF, which is an average over the area for you to use there. So just to do that. So these are just graphic output to show what we can get from the image precision extractor at the different durations, right? From the 30 minutes, 1 hour down to the 1 week. And then this is anomaly. This here, I focus on the area in Nigeria. I'm from Nigeria for beds. And then we can see the anomalies here to see what really is happening when we have the peak and we have the troughs in terms of those years' precipitation. And then we also have tried to test the outputs, the raw precipitation using the North American Land Data Simulation System precipitation estimates, as well as compare it to, so because the NOAA uses the NLDAS to do their model estimations and all outputs. So I want to see how my image compares, and then I also have station, which also generated, which also retrieved, and then we also compare. So we see that the image is not too bad in terms of look at the KGE and the NST. These are hydrological times, which we use to describe how models are performing. And then we use that input to run hydrological models and see how the models we run for using HMS, which is a hydrological modeling software, for using HMS to generate discharge, right? And discharge are basically used to generate what we call the stage, and then we can do the flood mapping to see the flood extent. We want to see how the image, output from the image perform in the model compared to what the NOAA uses, which is the NLDAS, and we see that even though the pressure correlation was higher for the NOAA NLDAS, our KGE and NSCE was higher, which is pretty good agreement compared to the NOAA NLDAS. All right. Well, our work is not without challenges, right? There are challenges, and just what I want to focus here, right? So because we have short-term period, our data set is only from 2000 to date, right? So we don't image is not available before 2000 because we are inheriting data set from the trim, and you know, we also want to, if we can improve this in the future, it will be to the capability for users to bring in, import their own watershed, import your own shapefile, and be able to get the precipitation around that area. So there are many areas we can improve this, and then also extract longer precipitation time series. So right now you can get precipitation, I think, for 3 months at a time before it times out. All right, the second web application I want to talk about today is Rapid Image Viewer, and this is where most of the support I got from the American View went into. This is a very cool tool because this tool is very good for validation, right? So when we generate flood maps, for example, we use the JUICE flood plane model to generate flood maps, and then we want to see how those what areas agreement are with satellite. So the Rapid Image Viewer gives us historical and current, or sometimes even near real-time remote sensing images, so you can download them. And I'm going to show you what kind of data set you can get, and how we've used them for different hazards, to monitor different hazards. So here we can see how we can use. So this is showing areas where we have water extent, which is the blue areas, and basically This is basically used for validation and reconnaissance, as the case may be. The rapid image viewer, which is image-based web application, is really cool because we have this range of data sets from the NAPE data set. We have the Sentinel one, so which are the NAPE is 1 meters resolution, really cool. We have the 10 meters from the Sentinel, and then we have 30 meters from the Landsat. We also have Motis and right at different. So these are very good because we have both the optical and the radar sensors working together. And you talk about the Sentinel one there, which is a radar. And then we also have the ability to get the data out as RGB true colors and also as near infrared. We can segment, we can get water index to see how water extent. We can also do those thresholding, which I'm going to show you. And we are leveraging from long term because we have data set that come all the way from 1984, right? We can see from the 80s, we can see some data out to date. Some are still, why some are out of date, some are still, majority of them are still present. And the NAPE can be here and there, right? Sometimes it's not always consistent yearly, but at least we can find years where we have data set and use the data set to do what our research or what we want to do with them, right? This is the interface of Rapid Image Viewer and similar procedure with the image presentation extractor, right? The cool thing here is that you can go anywhere and draw your rectangle and it will filter based on that location, and we have information about the data set, which will keep updating. And then we can always get those data sets in different formats. I'm going to try to demo this. So how have we used the Rapid Image Viewer? This is an example of flood. So we have used it to look at floods to see what is the flood extent like, right? So in the Rapid Image Viewer, you can actually have the pixel count of the flooded. So within the box we draw, we can see how many pixels there have been flooded and how many out of the total pixels we have and how many were not flooded. So we can see that. So this is an example of using it to look at the 2019 Great Flood of the Midwest, right? So this is the John Redmond Reservoir and the Neosho River, and these are in Kansas. So we look at these 2 days. This is May 22nd, 2018, and this is the same May 22nd, 2019 when we had the flood, and we can see the flood extent has increased. Like I say, we can also get the exact pixel counts, and we can do that. We've also used it to look at other places where we had flood issues. Like the first one here, we had this. This is the Turtle Creek. So we can see before the flood, and we can see after the flood. We can see how the stream banks kind of water kind of flooded those areas, and we can see the extent. And we've also used to look at some other areas like the Missouri. We have the Omaha, and you can see the flood. You can see before the flood, and see after the flood. You can see the extent. So this is really cool database where we can see how our environmental resources are changing, and how we can make decisions from there. We can also aggregate those time images and create time lapse of resource change. For example, here we are trying to see how long-term drought is impacting the Great Salt Lake from 1980 to 2022, right? We want to see, and we found out if there have been over 50% decline in the lake area. And I think I have here. So this is the time lapse we created. So we can see from 1980 down to 2020. When we compare these 2 images, 1980 to 2020, we can see high changes. So then that's kind of raises curiosity as what is happening there. Is it purely natural change? Is it human induced, right? What is really going on? So we can ask those questions and raise curiosity for more research to look into what's happening there. So those are part of the benefit of what we get from using the Rapid Image Viewer to see how there's been drought there. At fine resolution, especially if we can leverage the NAPE, we can see how our agricultural areas, like for example, this pivot, how they are changing, right? We can see, we can monitor how drought is impacting crop yield and all that. And those are very important for agricultural assessment. We want to see how our farmlands are performing due to climate change. We've also used it to look at fire, right? This is the 2021 wildfire in California, right? So I kind of label those dates 1, 2, 3, 4, and we can see before the fire, during the fire, we can see how the fire intensity is increasing. And this is one of the largest fire that happened in California. In fact, the first fire that crossed across the crest of the Sierra Nevada, and that cost over $637 million to kind of combat. So it was really intense. And we are not just limiting the rapid image viewer to the US. We can also use it to look at other places around the world. For example, here we used to look at the wildfire in Australia, Victoria region in Australia that occurred in 2020 due to the 2019 drought, intense drought in Australia. So you can see how intense even the fires are, right? This is before the fire, and this is when the fire is actually when it's still burning, the forest is burning. So we can see all that. We've been able to apply this rapid image application to other areas like vegetation change, right? We can see this is the Nigerian kind of greenery. We can see how seasonalities and all that is changing due to if we use those Motis, we can be able to see how this the greenery is changing. We can I've showed you this earlier. Also, we can see, so here, this is the Lekki, the third one here is the Lekki expansion in Nigeria. So we'll see how they're kind of creating land from nowhere, kind of dredging the rivers, trying using that to build, to expand the area. So if we put those images together, we can see those changes, those expansion in those areas. And this is really interesting because help us to plan very well and know how those environments are changing. There are a lot of strengths, weakness, opportunities, and threats in using these web applications, right? Maybe I'll just talk about one from each of them so I don't take all the time. It is fast and easy to use, and because the programming skills, you don't need the programming skills to use web applications, which are really cool, right? But then you also need knowledge, just a weakness of remote sensing, and you have to maintain the workflow, which is cool. We have global coverage. And that is one good thing in this web application, right? We're not limited to one location. We can see patterns, so we can be able to study those patterns. And one threat is that we need an external body to host our web application. Like right now, we are hosting on Google, and hopefully Google keep having the power to keep us, and and then in years we still have the capability to run this. And then we need to be able to have we always think that we have internet, right? But we know that not everywhere in the world people have this good internet or whatever to do this. So this could also be part of the threats there. But we have other additional tools that we have developed. Like I mentioned earlier, we have the PMP calculator for deriving probable maximum precipitation and for modeling extreme flood. We also have the rapid forcing retrieval, which is cool for retrieving reanalysis dataset for hydrological models. The other project I've been involved, this current project I'm doing is for the NSF. This is extreme weather event mapping. So we're looking at historical weather event and looking at the wildfire, the blizzard, the ice storms, tornadoes, flood, wind, hail, and we have this data set already organized, all right, in a repository at the CAS site, and this is available for use. So if you ever need some of these data sets to see what's happening in Kansas, you can reach out to us. We can be able to provide these data sets for you. My other research also cut across probable maximum flood modeling. So I'm looking at different watersheds to see what is the worst case scenario of flood, what areas, what is discharge, and what areas will be impacted by the flood. So those are the kind of research I'm into: flood, extreme events, remote sensing, GIS, and all that. And of course, I've had tremendous support, and I want to acknowledge every kind of agency, body that have supported my research over the years: the Kansas Water Office, KDM, the Kansas Water Office actually is they funded the rapid image viewer from scratch, and then so with support from the KDM, and then by the Google Earth Engine that I am hosting my dataset, CARS, American View. I can talk about my work without the support from you all through Dana, and then the National Weather Center, Office of Water Predictions, that also supported me through internships and getting experiences for the models. And a lot of them, they CAM, the RISE project. So just to conclude and take question again, the environment, these web applications are very important, right? They are very important because we want to see our environment, we want to monitor changes, and we can be everywhere at the same time, right? We want to see what's happening where they're happening. We don't want to be domiciled or restricted to one location. We want to see if the changes happening in the environment are also happening in other places, right? What is peculiar in those places, and how can we use those information to predict or to plan for the future? And that is why this research is very important to me and to my group. And with this, I hope I'm able to stop now to take your questions. Again, you can always reach me through any of the emails there if you have questions I'm not able to address here. But thank you very much for your attention.
Thank you, Kenneth. We do have a couple of questions in the chat. Tom is asking from USGS, how is the cross-calibration of platforms performed? For example, when doing vegetation change monitoring? Yeah,
this is a very good question. So the rapid image area, when we started it, the focus was on water to kind of provide remote sense image for validating our output from the floodplain models, the flood maps we are generating. And that is why you see we are more focused on the, let me see if I can exit. We're more focused on the NDWI, since Chen was working on the vegetation side, but we can download real image, and from the images you can do your NDVI. So right now what we have is the NDWI. So I don't know if you so basically, to answer in short, we don't have we didn't focus on the NDVI to look at those vegetation, but we have the data that you can use to monitor that, right? We have those data. That's what I was showing here. So we have the NDWI, but we don't have the NDVI, and we can easily add the NDVI if the need be, but we can create the vegetation monitoring system. So, because we have the data set already from all the necessary satellite we can get hand of.
So Tom also asks, when doing work in places like Nigeria, is there a dependence on detailed knowledge of the hydrography? Is there a need for improved DEMs?
That's a good question. So yeah, we look into all our DM that we use, and I think right now my research is focused on Kansas because but we try to provide a scalable product that we can apply to other places. So yes, we also take into account the hydrography, and we need to improve the DEM. Of course, we need to do those DEM preconditioning, right? We need to fill things and do all that. So yeah, we do that.
Okay, and then Carter has a question here. Is the precipitation data readily available through NASA or USGS? And what is the resolution of this data set?
So very good. So let me start. The data set is, when we finish this project, we handed all you need is a URL. We handed the URL to them, and we still have a couple of stuff to do. Like I said, we want to expand the anomaly estimation up to 20 years. Right now, it's annual. So we want to do it for the multi-decadal, so we can see how those two, we still have some improvement to make, which is what we are working for. Resolution, the IMERGE data set is 11 kilometer, but the beauty of it is that it is ground calibrated, right? So there are a lot of improvement going on, and the app is there. Any improvement in data set will be inherited. The app will inherit those improvements, and as everything keeps getting better. So we keep validating it. We keep making sure that the results are good. Yes, I'll be able to. I'll be happy to share. As a matter of fact, I need to share my. So I will just share the repository so you can see all the applications and can use. And they're available on the ARCOP website. Yeah, thank you. Thank you, Dana. Okay.
Okay. I believe Tom had an additional question here.
Yeah, water for space effort might be rising out of pieces of water over time. Yeah, I have not looked into that, but it's going to worth me, because most of my projects have been need based, right? So we're always looking for good products like what you mentioned now to validate our work and see what we can get. But one thing that is peculiar to us is we are looking at data sets that are also that have global reach, right? Most of the fine scale data sets, they are domiciled in the US, so North America and other advanced Europe. So yeah, they are good for validation. So this will be very good. Thank you for mentioning this one. I appreciate that. It's American View tied to this project currently. So we've received, I've received a one-time support during the rapid image viewer. So of course, I can give you guys the credit because during the course of this project, I received the support for this. But the work has been purely funded by the Kansas Water Office. But there's support here and there on ways to improve it. Like you can find ways you want us to improve this, and if you think of funding us more to add one or two features, we can be able to do that through my boss there. I don't know how it works, so I don't want to speak more into that, so I don't get into trouble. But you can always speak to Dana or Jude, and there are more things that can be done there. Okay.
Kenneth, do you have just a minute to maybe demo the tool, one of the tools?
Oh yeah,
for
yeah,
us?
yeah. Let me do that. So this is the. Let me start with Rapid Image Viewer. I like picking this location, but of course we can pick other location to see. Say for example, I go into. So once you center it, it's going to draw it and then put a rectangle so the processing. The beauty of this is what it does is when we draw the rectangle, it kind of set the filter. So you use this rectangle to filter images within this location inside that box. And but when it's downloading, it's going to only download the extent of the crop. So we can see image. Let me show you an example. Let's say we want to see what's happening here in the year 2000, and then we're going to look at Landsat 5. So we have the Landsat 5 true color. Let's see. So this is basically saying that we are going 30 days. So looking at all the way from maybe the end of August to 28th of September, and that is what this 30 days means. So it's looking at prior days. So you can set that time window. If you want to take it over a longer period, you can do that. Right now, the RGB may not make sense. So we can switch to look at the first color and see how it does look like. And it's going to clear the first selection. Okay, it's becoming clear. We can see more the water area, and we can also look at the water index to see. And if the water index is kind of choppy because maybe it's picking some other land features, so we can also look at this cool one, which is the water edge, which exactly find the water pixels in that image. And this is the water extent based on the period. Maybe if I go to more rainy days, I'm going to see more water cover, but we can then compare that with what we have today to see those changes, and just take a look at this extent of the water, and let me run the current day, which is the Landsat 9, what we have currently, and you can see how the water is reduced. Of course, we can look at the Landsat 9 water edge and see. So we see that great reduction. We see that looking at the past, and we see a lot of high water loss to this extent, and that is what we're talking about, the problem of climate change. We don't know. I've heard of harvesting. What's what have been highly used by farmers, and there are a lot of studies around why this water is changing, which I don't want to go into now. So that is one cool thing. So I like using water, for example, to look at it and to see how those are changing. And of course, we can also look at the image precipitation extractor, which is also what we have there. See, so we can find all the USGS stations in the US and find what precipitation from that intersect with image that we have there. And what we need to do is to drop our points. Let's say I want to use this. So I drop my points in that location. It could be a miss or hit, so it's always okay to keep trying until we could get, okay, it's relatively close. Let's see. So with that, we can define our window of extraction. Right? This is one week. This is from the 31st of August to the current date. So the app is built to self-update to current dates. So it doesn't matter if you use this in 2 months' time, it's going to give you the exact date record you have. And then we can pull the data in 30 minutes. And yeah, of course, it's good. Having said to export raster, we can export raster because it is a point data. But if I draw a polygon, which I'm going to show you, we can export that area. So this is a 30-minute precipitation for the time period that we have for the window. And of course, we can aggregate over longer periods. Let's say we can do it for every 24 hours to see. So it's going to do an internal accumulation and go at the 24-hour window and give us the precipitation. One more thing I want to do is to show you, and of course we have the global gauges from the NOAA, which you can use to get for other locations. We also have the if you want to get by country, you can be able to get the draw by the country, you can digitize that, use this polygon to digitize. You can also get for the hydroshed, tells us more about the watersheds. See, make it clearer. So with this, all we need to do here is basically say we select the watershed we want. We can digitize, we know the location, and we can search location by using the search bar. So we have the search bar, which is here. So we can search for locations by search for places, search places. And with the area I draw now, so I can be able to get precipitation for, let me say 1 hour for the time period. So it's going to aggregate the kind of pixel weighted, but it's based on the weight of the pixel that fall in the watershed. Is going to calculate the watershed precipitation and give me the output. And we can also download the data. So this is the weight over the spatial area. You can get it. One more thing I want to show is say the storm, and keep mentioning the storm, what I mean by the storm, so we can put that in context. So for this 30 days or 29 days, we can see the storm that passes through the corners and know what is the nature of the storm. Yes, everyone goes to Great Salt Lake. Thank you. Yeah, so we can see the storms pass. This is the first image. Kind of leave the first image there. Let's see and we can track the cyclone, is there anti-cyclone direction that is moving. We can see the intense area. So we can do a lot of more improvement. We can even let it inherit the boundaries of the corners, which is also very good. So we can see where exactly we can pinpoint our location. So our app is there. There are a lot of improvement that can be made. The most we focus on need and how our users want to be able to get this output and what they want from it. And yeah, and I think there are other apps, but I just want to limit it to this. If you're welcome to play with the rest of the applications and see if you have questions, one email away, and we're happy to respond.
Does anybody else have any questions for Kenneth?
Kenneth, this is Chi Chen from Hawaii View, and I have a question for the rapid image viewer.
Okay.
When you try to like set up like the date filter, like let's say I put like 1 year for Hawaii, and check like Sentinel-2 image. So I saw the mosaic it generated. There's still a cloud. So I wonder like what kind of mosaic algorithm you used in GEE. So is you try to average all the images, or you try to
so that's a good. So we average them. We find the average for that period, and we have when you talk about the cloud, we try to create. If you can see, we had versions there. So because the project keep changing based on the need, at some point we wanted to create some cloud filter, and that is one area we can improve it in the future, is to allow users to know how much of cloud they want to see, or they want to see the entire image. So right now we are leaving it the way it is, because some people want to see the cloud, some people researcher they want to see the cloud where it is, and we want to add those capabilities maybe in the future so people can be able to. So yeah, cloud is part of what we, like you see in this image, we have cloud, and we want to also, maybe we can also differentiate the cloud from the snow area with time, and those are more capabilities we can add on the tool.
Okay, thank you.
Yeah. Thank you very much for that observation.
Thank you.
And yes, the mean is what we get. So we take all the images, we give you the mean. So if you want to see the exact image, you have to maybe reduce your time filter and go close to the period you want, and maybe you can see just one image. That image you can pick it. Okay.
Yeah, I understand. Yeah. Thank you.
Hi, Kenneth. This is Carter Wong. I just have a very quick question. So I see that here you have like Sentinel-2 NDWI, like the water index. So I'm wondering if you are planning to maybe add some more indices like NDVI or or EVI indices.
Yeah, that's a good question. So we thought of doing that, and maybe in the next version, or when we, of course, try to, which is something we're also thinking about. We can add more indices. There are many indices, like even fire index, drought index. We want to be able to add some of those ones and see how we can use that information for other areas. But right now, the rapid image looks to me to be more helping those who are in the flood areas, water related. Yeah. Of course, I really appreciate your catch there. We have that in our radar and try to improve on those areas. But we have other tools that deals with vegetation. Maybe we can, if you go to the CARS or the CARS website, you have the one Chen built, the vegetation one. So those are also, but that's not my tool, so I can't talk about it. But we have several of those tools.
This is a very cool kind of tool. Thank you so much.
Yeah. Thank you.
So I put the links to Kenneth's work in the chat, and he also included his bio that I distributed to the committee's email. If you have any further questions for Kenneth or some feedback after you take some time to play around with his tools, I'm sure he would greatly appreciate that. So we are 2 minutes shy of our hour. If anybody has maybe one last question for Kenneth, otherwise we would like to thank you, Kenneth, for presenting today and showing us some of the cool apps that you've been working on.
Thank you, everyone, for having me. Hope I can come again next time. Okay.